me introduce the speaker. Dr. Marcus Ruiz received his bachelor's in mathematics from North Dakota State University. Oh, nice. Dr. Ruiz moved to the Boston area soon thereafter to attend Northeastern University. Good school, where I got my Bachelor of Science degree. Dr. Ruiz received his PhD under the advisement of Dr. Jerzy Wyman, a pillar in the field of representation theory and algebraic geometry, with a thesis titled Standard Basis for Coordinate Rings of Cotangent Varieties. 4 years ago, Dr. Ruiz joined the ELC community. He is seen being credited for his new approach to pedagogy and the unique nature of some of his math classes. So some students will tell you these classes are hard, but that might be a good thing. He has recently offered special math classes in the area of cryptography and differential geometry, and continues to work on several future classes and projects in conjunction with physics and engineering. So, without any further ado, welcome Dr. Ruiz.
So, my goal in the lecture today is to try and just give a gentle, i.e. computational introduction to some of higher mathematics. And try and maybe just give you a bit of the flavor of what it is that I'm trying to do. And where we're going to start is a structure called SL2. And, well, any good math presentation begins with a definition. So SL2, and we usually put C here, or you can talk about R, whether it's over complex numbers or real numbers, is the set of all matrices, A, B, C, and D, with the condition that A plus D has to be 0. So really we could rewrite this as all matrices A, B, C, minus A, and there's no other conditions. So the trace, or the sum of diagonal elements, has to be 0. Up until now, we're just talking about matrices, but what makes this different is the following thing. Well, first of all, we can add two matrices at this point. And we end up with a matrix that has the same property. Right, the diagonal entries add to 0. But the thing is, we can't multiply them. So if you have two matrices such that the diagonals add to 0, their product isn't 0. So this set isn't closed under multiplication. So as an example, right, this matrix is in SL2, but its square is not. So this isn't closed under multiplication. So what we actually do is we're going to introduce a different product. So instead of doing standard multiplication, we're going to introduce a notion of bracket. And this is called the Lie bracket. And it's the following idea, that we take two matrices, A and B, and instead of looking at their product, we look at their commutator. So we take A times B, and we subtract B times A. This has the nice property, and it's a fun little exercise. So the proposition the bracket is inside of SL2C. So if I start with two matrices in SL2, I take their Lie bracket, I end up with something in SL2. So SL2 is closed under bracket and addition. So these are the two operations we're going to consider. So one of the things we care in mathematics is how do you build something? What's the smallest number of pieces I need to build a structure? In the case of SL2, I can build it with three distinct elements. They're called E, F, and H. So we let H be the matrix 1, 0, 0, minus 1. E is the matrix 0, 1, 0, 0. And F is the matrix 0, 0, 1, 0. Now, the reason these build everything in SL2 is that if I take a generic element, so A, B, C minus A, I can write it in terms of H, E, and F. This is equal to A times H plus B times E plus C times F. So everything can be written in terms of these three elements, E, F, and H. So to understand SL2, what I really need to understand is what goes on in E, F, and H. So we really want to know understand these three elements, E, F, H. Well, we see how to add them. They add very easily. We just add coordinate-wise. What about their brackets? So what happens with the brackets? Well, this is direct computation. I'll do one of them, but then the rest of them I'll just write out the answers. So EF, what is this? This is the product of E times F minus F times E. So that's 0, 1, 0, 0 times 0, 0, 1, 0 minus 0, 0, 1, 0 times 0, 1, 0, 0. Well, remember how you multiply matrices is row times column, and row times column. So when I go through and the smoke clears, I get 1, 0, 0, 1, 1, 0, 0, 0 minus 0, 0, 0, 1. This is 1, 0, 0 minus 1, but that is exactly H. Let me move these up because I don't need them. So what we get is we get one of the products. E times F, or E bracket F, is H. H bracket E, that's not hard to compute, is 2 times E. And H bracketed with F is minus 2 F. What's interesting is now, instead of talking about this in terms of matrices, I could have just said SL2 is the space of all things of this form. So all sums where I multiply a constant times H plus a constant times B, constant times E equals a constant times F with these relations in the bracket. That's in fact all the information I need. So this leads us to the notion of what is called isomorphism, and that's when we're trying to say that two things that may look different are in fact structurally the same. And what I contend is the following. So this is a what I like to call a fluffy definition of isomorphism. Right? So two things are isomorphic. If they are functional. Right, So in terms of their function, I can't distinguish them. I may be able to distinguish them by how they look, but really in the way they function and the way they behave, they are in fact the same. So my contention is the following. Well, let's look at the following. So instead of looking at matrices, we can go to an entirely different world, and we can look at the world of calculus and derivatives. So let's consider the following example. Let's consider all things of the form. So let's consider two main elements, x and the derivative with respect to y, and y times the derivative with respect to x. So this is x times the derivative with respect to y times the derivative with respect to x. Let's look at the commutator. So the commutator, or the Lie bracket, x, the derivative with respect to y acting on y times the derivative with respect to x, minus y times the derivative with respect to x acting on x, the derivative with respect to y. Well, the only interesting thing that happens here is we differentiate y with respect to y, we get 1. So these two terms cancel out, and so we're left with x dx minus y dy. So I get a new element. I get something different. Let's continue taking on. What do we get? Thoughts? We can expand it. And you compute. Well, the only thing that survives here is the derivative with respect to x is 1, so I'm left with x times the derivative with respect to y, minus, the only thing that survives here is this term, so I get a minus x times the derivative with respect to y, so I get 2 x dy. The other one, the other commutator, which I won't compute off explicitly for you, this one ends up being minus 2 y times the derivative with respect to x. And so we stare at this for a minute. Right? We're trying to understand these different derivative operations. We want to see what is this with the Lie bracket. And we start to notice something. We see that when I take the Lie bracket of these two elements, I get a third element, something that looks new. When I take that new element and take the bracket with respect to my old elements, I either get 2 times the element or negative 2 times the element. Well, we've seen that before. Those are exactly the relations for SL2. So we're able to identify, so we can make the identification can identify these with SL2. And we have to do it in kind of consistent fashion. So the product of two things giving us a third, well, these two things have to be E and F. We know that. And so if this we can set this to be H. So let's pick H to be x times the derivative with respect to x minus y times the derivative with respect to y. And now I have to look. Remember, H bracketed with E. H came first, and I got 2E. So I look where H goes first, and I get 2 times the result. That means E has to be x times the derivative with respect to y, and F has to be y times the derivative with respect to x. But it turns out all information is preserved. So essentially, at a real fundamental level, this is SL2. Right? I cannot distinguish them except for how I wrote them. Right? Functionally, they are the same. So this gives us what is called an isomorphism. Right? It's a way to identify two things that are structurally the same. So if we can have lots of things that are structurally the same, how do we really identify them? How do we characterize them? So what is it that really characterizes SL2? And one approach that mathematicians use is we look at what our object does to other objects. In other words, how does it act on other things? And so what we can do in this case is we can look at how my differential SL2 acts on some set. And the set we're going to consider is the set of homogeneous polynomials. So let's set V sub d to be the collection of polynomials in two variables of degree d. So it's xd minus 1 times y to the first, x to the d minus 2 times y squared, all the way down to x to the first, y to the d minus 1, y to the d. And I can consider all possible. Yep.
Is it the set H and F isomorphic to SL2 or set H and F plus the bracket operation?
You need the bracket operator. Right? So it's the three elements E, F, and H with the bracket.
So that's the same thing for the application.
Right. So over here. Well, now see, the other thing that we have to pay attention to is that this identification preserves brackets. So if I do the bracket on this side, or I do the bracket on this side, I get the same result. Right? The identification still fits. So really what we're going to look at is all possible polynomials of this type. But as with anything in calculus, it's linear, so I can just look at what it does to individual pieces. Right? When we differentiate a polynomial, we don't just differentiate the whole polynomial, we look at the individual monomials and differentiate them. We're going to do the same thing here. And so what we want to know then is how do my E, F, and H act on the elements of this set? What do they do? Well, again, this is a computational problem. So let's compute. So what does x d dy do to x to the d minus I, y to the I? Well, I come through and I first differentiate with respect to y. So I get x times I, x to the d minus I, y to the I minus 1, and then I multiply by x. So I get I times x to the d minus I plus 1, y to the I minus 1. But what's important to notice is that I stayed inside my set. So really what happened degree of x by 1 and decreased my degree of y by 1 and picked up some constant. What about my f element? What does that do? Well, we can actually kind of guess. Like, if E moves me to the left, F's probably going to move me to the right. E and F seem to have kind of a symmetry, and that's not good. So differentiate with respect to x, multiply by y, we pick up a d minus I, x to the d minus I minus 1, y to the I plus 1. Matching our guess pretty well. And lastly, what does h do? Well, I split this up. So I differentiate here with respect to x, then multiply by x. So the only thing that happens is I pick up a constant. Differentiate with respect to y, multiply by y, I pick up a constant again. So the question is, what constants do I pick up? Well, in the first case, I get a d minus I. And in the second case, I get an I. So the end result is I stay exactly the same, except if I pick up a multiple of d minus 2i. Well, that's cool. Those of you that have had linear algebra know that what is really happening here is what we're saying is that x to the diyi is an eigenvector for the operator. As I stay exactly where I am, I just pick up a multiple. We can summarize the action in terms of a kind of a nice diagram. I'll draw for you. So I can add in arrows for each of my actions. And I can make this a very exciting presentation and switch of colors. So the action by F, what does F do? Well, F, that was y d dx. I differentiate with respect to x, or I move to the right, and I multiply it by d minus I. So F takes me this way, and I multiply by d minus I. So Here I multiply by d. F takes me this way. I multiply by d minus 1. D minus 2. Coming in here, I multiply by 2. Here I multiply by 1. And here, where do I go? So if I differentiate y with respect to x, I get 0. I go off with 0. So that's what f does. We can throw in the action of e. Remember, e moved me to the left and multiplied by I. So in this case, here's e, I multiply by d. I multiply by d minus 1. Here I multiply by 3, 2, 1, and I head off to 0. And lastly, I need to put in the actions of h. Well, h just takes us from where we started to, takes us right from where we started to where we are in. Except I multiply by d. Here I multiply by d minus 2. D minus 4. Going here we multiply by 1 minus d minus 1, so I multiply by 2 minus d. And here I multiply by negative d. So that's the whole diagram for the structure for how SL2 acts on this set. So we've summarized everything in one nice picture. Always good. So what we want to do now is this is a very kind of particular example. Right? What is it that's really going on under the hood here? And as I said, one thing we care about is two things that are functionally the same but may look different. So this particular incarnation of SL2 acts on this particular set in this way. So what is the essential ideas that really categorize how SL2 acts on something? And so that's what we want to kind of tease out and get our hand on. So we need to abstract a little bit. And the abstraction we make is we need to, first of all, just say kind of what is a general set that something like SL2 can act upon. And that set is what is called a module. So a definition. An SL2 module is a set M with an operation plus satisfying well, if I add two things, I had better stay inside M. Addition is commutative, so it doesn't matter the order I add. Addition is also associative, so how I group things doesn't matter. Or there has to be a 0 and it behaves just like you expect 0 to behave. add 0 to something and say that's something. There are negatives. Right, so for each m in m, there is a negative m, such that m plus negative m is 0. So far, I haven't brought in anything from SL2. What we want, then, is the following.
And Marcus, before you go on to that, and can you use the multiplicative operator instead of the sum? Or do you ever try to pick the operator to do the sum?
You need it to behave like sum, like addition. You could do something like a multiplicative structure, but then you would end up with the product rule at some point instead of. So there are. I want the sum to agree with addition in SL2. That's part of the thing. So it needs to agree with the operation here.
The bracket operation is not commutative, so it doesn't match up with your
Right. The bracket operation is not commutative, and in fact, it's not associative. So it's an example of it's a very interesting piece of its own right. We'll get into that further. So the fourth thing we want is that for any m in m, all of E times m, F times m, and H times m are in m. So I can multiply by my basic elements from SL2. This gets along with addition. So, in other words, E times m1 plus m2 is E times m1 plus E times m2. Similarly for F and H. So it gets along well with addition. It also gets along well with addition in SL2. So if I have A times E plus B times F plus E, match this up with what I wrote originally, which was A times H plus B times E plus C times F times something from M. This is equal to A times H on M plus B times E on M plus C times F on M. So it gets along with the addition in SL2 also. And the addition here goes over to the addition again. It's the same. And lastly, we need to somehow say something about the bracket. Right? Because it's really the bracket that makes SL2 what it is. And it's the following. Is that the bracket of any two elements, so let's call them S and T, on M is equal to S on T on M minus T on S on M. And this is for all S and T in SL2. So the bracket structure goes over also. So this is what an SL2 module is. What we see, though, is that all of that is satisfied by this collection VD. Right? All of those conditions are satisfied here. So VD is, in fact, an SL2 module. So what we want to do then is, what can we tease out from our V sub D, our homogeneous polynomials in degree D? What can we tease out from that that really gives us the full flavor and structure of what SL2 does to something, or how it acts? And this is where I wish we had sliding boards. Well, one thing to notice, and we can see this, oh yeah, I forgot from when I drew this picture. One thing to notice is there's a vector, or there's an element that E kills. Right? There's something that E sends to 0, and there's something that F sends to 0. That's going to play a big role. So what we do is we define something. The definition: an element of M, let's call it little m, is a highest weight element of weight D if 1, E times M is 0, and 2, H times M is equal to D on M. So what is the role played by highest weight elements? Well, we can actually see it from this. XD in this case, E sends it to 0, and H acts by multiplication by D. So this is a highest weight element of weight D. The other thing to notice is there are no other highest weight elements. Right? There are no other elements that E sends to 0. E, F kills it, not E though. Right? We're saying E annihilates, or E sends it to 0, but we haven't talked about the F action at all. And this is where things get interesting. So let's assume we have a highest weight element of weight D. So let us assume that M has a highest weight element of weight D. So usually we denote this as a pair, M and D. So the element itself and its weight. So this is something where E sends it to 0 and H acts by multiplication by D. What does F do to it? The natural question to ask. And remarkably, just by having the bracket structure and the fact that we're looking at an SL2 model, so the bracket gets along with M, we can say something about that. What does F do? So if we consider, we can look just at F of M, but we can't say anything about it. It's just, it is what it is. What kind of stuff. So instead, let's look at H on F of M. Can we say anything? And as I said, and amazingly we can. Why? Well, let's rewrite this identity. So instead of writing bracket ST on M is equal to S on T M minus T on SM, we could instead write, well, we can actually bring one of these terms to the other side. And so we get that S on T M is equal to, bring this term to the other side, the bracket minus T on S. Okay. So let's apply that to H times F. So in that case, H is my S, F is my T. So this is equal to the bracket of H of F times M. Plus F on H of M. Well, H on F is negative 2F. So this is negative 2 times F of M plus F. But what does H do to M? Well, M is a highest weight vector of weight D. So H times M is Dm. But D is just a constant. It's from the complex numbers. So this is negative 2 F times M plus D times F on M. And we can rearrange this to D minus 2 F of M. So what does this mean? Well, it means that H acts on F, on Fm, by a multiple of D minus 2. That's exactly what it did here. Because this is F on that. And H acts by a multiple of D minus 2. So just the existence of this vector, just having this highest weight vector, in other words, this vector that E sends to 0 and H acts by a multiple of D, is enough to really specify which collection V sub D I'm looking at. Right? All I have to do is find the vector that E sends to 0 and H acts by scaled-on, and I know which of these I'm looking at. Which is kind of cool, right? So we went from this very complicated structure of a specific example and have now distilled it down to 2 pieces of information. I think that's easy. So now that we have a handle on this, we should make a problem. So we can look at SL3. What is SL3? Well, one of the forms that it takes is 3x3 matrices. and trace 0. So A11 plus A22 plus A33 has to be 0. And here again, we're talking about the operations of addition and bracket. So bracket preserves the fact that the sum of the diagonal elements is 0. An exercise for you. Let's consider the operators x, d dy, x, derivative with respect to z, y, derivative with respect to x, y, and the derivative with respect to z, z and the derivative with respect to x, z and the derivative with respect to y. And so we take these 6 things, 6 elements, and we run them through brackets and do all sorts of work with them. This is another kind of way to generate SL3. So whereas we did it with derivatives before, we can do it with derivatives. So the point is, there's more than one way to view it. Really, what is the fundamental ideas? Well, SL3 is really generated by 6 elements, and they have the following properties. So generators. In other words, what are my really fundamental building blocks? Right? If I really break it down as far as I can go, what are my building blocks? Well, there's 6 of them. There's E1, E2, F1, F2, H1, H2. And they have the following brackets. H1 bracketed with H2 is 0. H1 on E1. Well, it turns out if the 2 lower indices match, in other words, if it's both sub 1 or both sub 2, it behaves exactly like SL2. So this is 2 times E1. So H1 on F1 is minus 2. F1. And then we have H2 on E2 is 2 E2. H2 on F2, which is 2 minus 2 F2. So the interesting ones occur, what about when I mix them? So what about H1 on E2? Well, this is negative E2. So I just multiply by a negative. Mixed indices get multiplied by either a 1 or minus 1. And lastly, what about E1, F1? Well, the bracket here is H1, E2, F2. Bracket is H2, and the mixed vanish. Now, one thing I'm missing, there's a few brackets that are just the bracket itself. We don't really express what it is. But what you can do, so the brackets of like, who is it? E1 with E2. I didn't list those here. They are just what they are. They're just the bracket. Turns out. You can call that E3 if you want. And it corresponds to this upper right. compute everything just from the equations that I've already given. So, how do I determine actions of SL? In 2 minutes. Well, the big thing to realize is I have 2 H's now. And I have 2 things that are diagonal matrices. So, I'm not going to just have a single. Well, I mean, what does it mean to be a highest weight vector for SL3 now? So if I have an SL3 module, so you just, the definition that I gave for SL2 modules, just take the same definition for SL3 modules. Not much changes. But what is the highest weight vector or element for an SL3 module? So M in M is a highest weight element. Of weight, and here's the thing, we need to specify 2 numbers. We'll take mu and lambda. If, well, we now have 4 conditions. E1 on M is 0. E2 on M is 0. H1 on M is mu times M, and H2 on M is lambda times M. And what I'll end with is you can draw a similar diagram that we drew here. But the question is, how do the weights move? So here, we go from weight D to D minus 2, so the weight decreases by 2 every time. How do they move for SL3? Well, if you have weight mu lambda, so the question is, what happens as I go this way? So if I move by F1, or if I move by F2, what is my new weight? In other words, how do H1 and H2 act? And you can compute all of that directly from these relations. So let's compute one of them, and I'll leave you with that. So what is H1 on F1 of M? Remember, this is the bracket of H1 on F1 of M plus F1 on H1 of M. When everything clears, we get mu minus 2 times F1 of M. So the weight here is mu minus 2. But what happens to the other coordinate? So let's look at H2 of F1 on M. Well, this is the bracket of H2 F1 times M plus F1 on H2 of M. H1 on F2 we have in our list. That's just F2. So this is F2 times M plus lambda, sorry, F1 M. Plus lambda F1. So this is lambda plus 1. So I decrease my first term by 2 and increase the second one by 1. Here I go, if I go by F2, I go to mu plus 1 lambda minus 2. And so I end up getting this 2 by 2 grid. But it is entirely the highest weight that determines the module you're looking at. And I think that's where I'll stop.
Question
abelian group in order to build your modules. Is that why you cannot use multiplication? I think the other question is, could you get away with another group that's not abelian?
Maybe, but you generally look at abelian groups. Right? Modules you assume are abelian. So abelian just means that additions can be, or the operation can be switched. So his question was the underlying structure of a module, and so in my case, the underlying structure is that of what is called an abelian group. And in general, that's obtained. There's probably some issues that occur somewhere with getting the bracket to work.
I guess you called U lambda weight there. You have ND over here in brackets. Do you call that a weight?
Well, this would really just be a vector of weight d.
Yeah, because I was going to say they're not the same, so you're just using.
Yeah, usually you specify the vector with the weight, but here I was just specifying.
I'm all right with you calling that a vector. Over here, you call this a coordinate.
Or an element.
It's called a coordinate and element. Okay, I'm a little bit better with an element. Okay,
Yeah, I was trying to avoid the word vector, but it just
that's all right. No,
I have to catch it in my mind and translate.
Lots of questions, right? I won't ask them now, but there's a lot of quantum mechanics in here, and
This is energy states.
that's right. That's they're raising the Lord operator.
Right.
They
So
sound like
yeah,
the same
if
thing.
you've seen quantum mechanics, and this is something I was thinking about maybe mentioning. This is the raising and lowering operators for the quantum states of hydrogen. So the quantum states of hydrogen are completely encapsulated here, or of a single particle,
Yeah, it's in each system.
or any system. Yeah.
I guess one of the things that we see about the mind is that mass operation, what does F do? How did you come up with that each FM equals that bracket? What's that?
That's from here.
So remember, one of the things is in a module that the bracket passes over to the commutator. If you rewrite this, solve this for STM, you get that relation. Probably. I don't know.
So could you build SL3 out of SL2?
Yes. SL3 is actually built on, well, kind of built on 3 copies of SL2. And it turns out that's one of the fundamental observations, that if you just go along a row, it behaves like an SL2 representation. Or just go along a column. It's that when we try to do this operation, that we get something. No, SL2 is usually complex.
Is SL3 linearly independent?
The basis elements, E1, E2, F1, F2, H1, H2, those are all linearly independent.
It was always the answer in linear algebra, so.
So I had to use vectors, so that gave you a clue. Good question.
When inserting an SL2 or SL3, do you have to always end an SL2 or SL3?
Yes. Yeah. We assume closure. The operation keeps it. did a very nice job applying it to elementary particles. He started looking at, actually, there's what are called fundamental weights, which we haven't gotten into. But he started to realize that quantum particles had kind of this weight structure to it when you hit them with either angular momentum and things like that. He looked at it. And so he started placing particles in a certain, well, a different Lie algebra. So these are what we call Lie algebra when you have a bracket on it. And he discovered that there were one or two missing that were empty. So he guessed what those would look like just based on the math. And he was like,
Energy in the spin.
yeah,
Triangle, and there was one missing.
right. Yeah, well, actually, I think it was a tension.
There's a big minus.
Yeah. And he discovered one of them was missing. And so he was able to predict what it would look like, and then they went and looked, and yeah, there it was.
You know, it was there in the data all the time. They hadn't looked for it because they didn't expect it.
Right. The Lie algebra is interesting that it also occur in differential equations. They occur kind of all over the place, just in disguise. Hence, why you have to look at what they're doing, as opposed to what they look like. So that's in fact where they originally occurred, is they were looking at differentials and differential equations. Well, that's one of the early places.
Okay, should we thank the speaker again?